Hi guys, today we're going to be talking about independent and dependent events. So, events are independent events when the chance of one event happening does not affect the chance of another event happening. For example, you roll the same die, but you roll it 2 times, right? So the first roll does not affect the second one. 2 events are dependent when the chance of one event happening does affect the chance of the other event happening. So let's say you have a bag of like 7 different colored marbles, I should say, of 7, right? And you pick a blue marble and then you pick a green marble and like you don't replace it. So what's the chance of you having a blue and a green marble in your hand? That changes, right? If we pick them separately. So let's talk about like our formulas then. 2 events A and B are independent events if and only if the probability that both events occur is the product of the probability of event A, which is their first event, and the probability of event B. Oops. Okay, you can probably shortcut to prob. So how does this look symbolically? We would write probability of A and B happening has to equal to probability of A times probability of event B happening. Okay. For dependent events, we're going to multiply the probability of the first event happening. So it still starts off probability of A, but it's not just the probability of B anymore, right? Because A has happened already, so we have to call this now the conditional probability of the second event given the first event. So what that looks like is this. We would write probability of B, but you have to show that A, that first event, affects it. So how do we read this? This is read as probability of B given A. And this is a probability that event B occurs given that event A has occurred, right? So event A has to happen first. So this is my first, and this is my second. And this is a little tricky for people, okay? So be careful. The first one comes after the second one because it's read as B given A has happened already. So let's go back and check from 10.1. We showed using sample sizes how to do this. And now let's talk about how to do this without sample sizes. And you guys were heading in this direction, but you were like, why does it matter? So the first thing you have to do is read your problem and decide independent or dependent, because that will change the formula and how you have to address the situation. So a student taking a quiz guesses the answers to 4 true-false questions. Determine the probability of guessing question 1 correctly and guessing question 2 correctly. This is slightly different than my last example because we talked about only question 1 and 2. So this will not be the same as that 1/16 problem we got. So first off, guessing on question 1 is not related to question 2. So I'm going to identify that this is an independent event, okay? Which means that this is just going to be P of A and B is the same as P of A times P of B, okay? And A will be question 1 and B will be question 2. Sorry, let's label. So then we can say that, well, if it's true-false, right, it's 1/2 times 1/2, which is 1/4, or 0.25. So far, so good? Now let's think about, and so I understand this is so much faster than drawing out the sample spaces, but that was to help prove that this answer is correct. And later we're going to do a word problem where the sample spaces are going to be important to help us organize our calculations. So a group of 4 students includes 1 boy and 3 girls, and we randomly select one of the students to be a speaker and a different student to be the recorder. Well, they can't be the same student, right? So the second girl that is selected does depend on who the first girl was, right? Because it can't be the same girl twice. So in this case, this is a dependent event. Because although I'm looking at the probability of A and B happening, once I select my first girl, event A, my second girl happening, the chance of it being a second girl, B, depends on who my first person selected is. Right? So let's think about how this works. There are 3 out of 4 girls, correct? Because there's 4 students, 3 girls. So in the first choice, I can pick one of the 3 students out of those 4, right? There's 3 girls. Well, if I pick a girl the first time, then the second choice is not out of 3 girls anymore. There's only 2 girls left out of now a total of 3 students. So this will be, oh, and I'm not even going to multiply. Like, I know some of you guys are thinking 6 over 12, but the 3's cancel out, right? And then the 2's reduce to 2, so this is 1/2, or 0.5. Okay? I don't have a problem if you multiply it out, but if you can simplify like this, great. So that matches our answer from before without drawing it out. And then this last one is girl first, then boy second, right? So this is still dependent. See if you can get your answer here. Now, it seems a little ridiculous to write this out every time, but this is going to help you, and it helps identify that, like, yes, something is changing. Okay? So hopefully you get from here 1/4 or 0.25. Okay. Check to see if that's what you get. Let's move on. I know I'm jumping straight into quote-unquote example 5, but this is matching the textbook, so we're in 10.2, and we're going to compare independent and dependent events. So let's say we randomly select 3 cards from a standard deck of 52 playing cards, excluding jokers, right? What is the probability that all 3 cards are hearts when you replace each card before selecting the next card, or do not replace each card before selecting the next card? So if I replace each card, like let's say I pick a card, put it back, then the second choice is still out of the 52 options, right? So this is independent. And on the previous page, we only had 2 events. So it was like saying hearts and hearts, right? But we can also have a 3rd event and hearts again. But since we're replacing, these are independent, so it's really just a probability of hearts happening times the probability of hearts happening times the probability of hearts happening. Okay. And so this is 13 out of 52 cards are hearts, right? So there's 1 through 10 plus jack, queen, and king. And out of 52, there's another set of hearts, and then 13 out of 52. You can also think of it as 1/4 for each one, right? Because hearts is 1/4 of all the cards. So that gives you 1/64 or 0.016. I didn't specify what to give me, so on the test or quiz, I'll be sure to specify. I'm just going to give fractions and decimals for everyone right now. So what happens when you do not replace each card? Well, now it's dependent, because the second card I choose depends on what my first choice was. Okay, so this is now probability of this happening is a probability of hearts. That first one doesn't change, but the second one is dependent on me getting a heart the first time, right? And then the third one is dependent on me getting a heart and a heart. So this will be 13 out of 52. If I take 1 heart out, we always have to assume that we've already picked a heart. That means I have 12 hearts left to pick from. Okay. Oh, sorry. And there's not 52 cards left. There's now 51. Right? And now that I've picked 2 cards that are both hearts, now there's 2 less hearts, and there's 2 less cards. Okay? Let's do a quick reducing fractions. This is 1/4. We can do 12 over 4 is 3. And then 3 divided by 51 is 17. So it'll just be 11 over 17 times 50. I know you guys can do this all on your calculator, but I want you guys to understand how to simplify fractions quickly. Okay. And this is equal to 0.013, I believe. Okay. So far, so good? The last part of this question will say compare the probabilities. Now, if we're comparing, that means divide them, right? To compare like this compared to that. So we're going to take 1 over 64, divide by 11 over 850. If you wanted to put this into one thing on your calculator, please use parentheses if your calculator doesn't do separate fractions. Okay? So that'll be 1.2. And what does this mean? Well, it's 1.2 times, and what do we write on top? It's 1.2 times more likely to select 3 hearts when you replace each card. Right, in between. So that's this one. So you're going to use it in the context of the first one. Okay, this last part, I know so far some of you guys are like, well, why do I need to show all this work, Miss Trey? I can just do this part in your head. Great, do it, but I'm going to show you like how to write it out, because even though we start with not needing that, eventually we need to know how to use the formulas and manipulate the formulas, as we'll see in example 7. So before we get there, let's talk about example 6. A quality control inspector checks for defective parts. The table shows the result of the inspector's work. So a part can be defective and pass, or defective and fail, right? Technically, if it's defective, it should fail, which is why there's more, but some of them pass. A non-defective part could pass or fail, right? So these are the things that are like, shouldn't be happening, but it does. What's the probability that a defective part passes? Okay, so the question here is, we know it's going to be the probability of something given that something else has happened, right? And so the question is then, which one is the one that I'm talking about? Well, something has to happen first for the second thing to happen. Okay, so first it has to be defective, and then it has to pass, right? This one is not asking like, what's the chance of something being passing and then being defective. So the first thing that happens is your first event, a defective part, right? That's what we're identifying as A, and then B is passes. So let's write this out. Probability of something passing given that it's defective. Okay, and this order absolutely does matter. So the number that you're going to look at is the number of defective parts that pass, defective passes, right? So I want, if it's defective and passes, and then I want to look at it and divide it by, given that something has to be defective, right? So total defective. So this means that I'm looking at 3, but I'm going to be dividing by everything that's defective. 3 plus 36, which is 3 over 39. That's 1 over 13. On my calculator, I would get a decimal, but let's see, 1 divided by 13. 0.077. So take a moment and see if you can do this one. Find the probability that a non-defective part fails. Okay. Pause the video here, and then I'll write in my answer. Okay, check and make sure that you got 11 over 461. Let's see. So as to fail and be non-defective, right? So the total is 11, and out of the total it has to be non-defective first. Last one. Finding a conditional probability. So now this is where the formula comes into play. So at a school, 60% of students buy a school lunch. Okay. Only 10% of students buy lunch and dessert. Oh, so there's two things happening. That means this must be A and B, right? What is the probability that a student who buys lunch also buys dessert? Okay. Now that means we have 60% is the probability of A happening. Okay. We have 10% is the probability of A and B, right? Lunch and dessert. And what we're looking for is the probability of never lunch given that you buy dessert, right? Because we have to talk about the second event. So this is my first, and then this is my second. So dessert happens given that they've already bought lunch. So how can we figure this out? Well, if you guys were doing things just based on like what you think is right, like just multiplying what you have, we're not gonna multiply these two numbers. So this is why we need to have a formula, because we need to know if we're multiplying, dividing, adding, or subtracting. So here's our formula. Since it's conditional, right, like something has to happen to affect the second one, we know we're gonna be using the dependent events formula, which is probability of A and B equals probability of A times probability of B given that A has happened. Well, look at that. We have 10%, we have 60%, and then we have our variable that we can solve for. So we have, let's see, just be careful here, 10% equals 60% times probability of B given A, and that's what we're solving for, and we don't know, right? So I can divide by 60%. Percents cancel out, zeros cancel out. So the probability of B given A, which means the probability of you buying dessert after buying lunch, is 1 over 6, which is the same as 0.167. Okay, we will practice more in class on Monday.